Right. My name is Kengo Hirata, and I'm going to talk about quantum if statement as in the former talk. But what we're going to do talk about is quite different thing, and which you might think weird. And this is a sorry. And this is a joint work with Takeshi Tsukada. Right. Oops. So in this talk, we're going to talk about a program which looks like this. And in this program, you see measurement and quantum myth. But there's an obvious problem that measurement appearing inside a quantum myth, which means that if you try to write down in a circuit, you get a program which looks like this. This is quite weird. But we're interested in this kind of program. Why? Because we have a motivating example which has something look like this, which is called quantum switch. So quantum switch is a quantum channel made up of two quantum channels, E and F, and it applies EF or FE under the control of a qubit X. But there's a problem that in most of the programming language, we cannot write this quantum switch. It's because most of the programming language refuse to write measurement inside quantum myth. We can only write unitaries inside this quantum myth. So you might there might be several explanations we have to have this kind of restriction. But technically speaking, from the point of view of semantics, we can say like this is because the semantics for quantum control channel is ill-defined in general. Well, but there's a quantum programming language called QGCL, which has quantum myth and measurement without limitation of measurement appearing inside quantum myth. Yes, this is pretty nice, and Ying had defined the semantics, but there's some remaining issues. The first issue is that in that semantics, we cannot know how to implement program into a circuit. And the second issue is that there's some ambiguities in the semantics. It means that there's a parameter in the semantics, and if you choose a different parameter, you get a different semantics. So the question we want to address in this talk is, can we define a clear semantics with simple physical implementation for such kind of programs? So what we're gonna do is to think about a language which is essentially the same as QGCL, but we're going to give a different semantics with different approach, and think about different semantics. Right. So what we're going to propose in this talk is a program transformation technique. And in this program transformation, given a program which has measurement inside quantum myth, we're going to transform it to a program without such kind of measurement. And the key idea we're going to use in this transformation is to defer the measurement from the inside of quantum myth to the outside. And as a result, we're going to explain that with this semantics tells that we can have an obvious physical implementation to a quantum circuit. And we want to explain that as an application, we can use this technique to give a semantics for a program which is something called like quantum control while loop. Right, so let me talk about the program transformation algorithm first. The language we want to consider has only two types, and which is quite simple. The one is the qubit, and the other is Boolean. And we have to use this qubit in linearly. And the example we want to consider is looks like this. And so this example, the idea of the example is just a quantum control measurement. But this program has a little bit problem. I mean, the outcome of the measurement has to be Boolean, but this P is qubits, so I just fix this type error, and we get a program like this. So what we're going to do is to transform this program into a program without measurement appearing inside a quantum myth. So the algorithm we're gonna consider it consists of 4 steps, and the first one and second ones are we're calling differing measurements. And the difference is that the first one only touches the program which is inside the quantum myth, and in the second step we're gonna move this measurement to the outside. And the third step, it's something we are calling introduction of dummy value, which makes our semantics also ambiguous. And the last step is not interesting step. I just gonna change the appearance of program for simplicity. So let me now move on to the first step. So first step, we changes a program which is only inside the quantum myth. So given a program on the left, we have measurement at the top of this block, and we're gonna change it to a program which measurements appears in the bottom. And the algorithm we use here is a classically known one. It means that writing this in a circuit, we're gonna transform a circuit on the left to the right, which is known to be equivalent in semantics. And in the second step, we want to move this measurement to the outside, but we don't know how to do that, but we just forced to move to the outside. So this is so simple. And writing this in a diagram, we given a program which on the left to the program on the right, just moving the measurement to the outside. Yes, so this step is so simple, I mean too simple, and which causes some problems. The problem is the type mismatch. So looking carefully this program, P0 in the then clause is not consumed because it's only used as a conditional of a quantum myth. But looking in the else clause, P0 is renamed to P1, which means that P0 is already consumed after applying this else clause, which means that P0 is used differently in the then clause and else clause, which is a problem. So looking the else clause, after running this else clause, we have to use P0 again, which means that we want to use P0 twice. So what we're gonna do in the third step is to fix this problem by redefining P0 just after the first use. So what we're gonna do is to insert the program on the right, which means that redefine P0 with a dummy value. What I'm calling a dummy value is an arbitral quantum state. So we're gonna choose a arbitral quantum state and insert the red colored line. So I mean, if we choose cat0, we get a program which on the right, and if you choose cat plus, we get a program on the right. And after applying the third step, we get a program which looks like this: control isometry followed by measurement. And in this final step, we just change the appearance to a simple looking one. I mean, a definition of initial states followed by controlled unitary followed by measurements. So this is not interesting. So let me summarize our algorithm. We first move the measurement in the then clause or else clause to the back. And in the second step, we forced to move to the outside of quantum myth. And in the third step, we fix the problem which is caused by the second step, which means that the violation of linearity. And finally, we change the looking to a simple looking one. And so this whole algorithm is quite simple, and the resulting program has obvious implementation into quantum circuit, which means that applying this algorithm, we get a quantum circuit, and so we get we know how to compile a program into a circuit. Right. So we did a little bit weird thing. So what we get as a semantics. First of all, this algorithm works well with quantum switch, which means that our semantics by this transformation technique defines the correct semantics on quantum switch. That's good. And secondly, we compared our semantics with Ying's original one. So let me review the semantics defined by Ying. So he defined two semantics. First one is the original one, and the second one is a kind of generalized semantics, which uses some parameters and if you choose a different parameter, you get a different semantics. And what we have observed is that, at least in the simple example we have explained, the choice of parameter in QGCL semantics is exactly the same as our introduction of dummy value. And we can give a different explanation for this parameter. I mean, we have to introduce this parameter for a pure type theoretical reason, and which is a new point of view. We also compared our technique with Abel et al.'s observation. So Abel et al. Observed that to define a quantum control channel, we need not only the clause of the compositional channels, but we also need the kind of more additional information of what they call initial state of environment. And what we have observed is that this initial state of environment is quite closely related to our dummy value, which means that we could found a non-trivial connection between Ying's semantics and what Abel has observed. So finally, let me explain how can we apply our technique to the semantics of quantum control while loop. So quantum control while loop, it's a program which looks like this. So we have we have two qubits and a quantum while controlled by a qubit. And M is a program which updates the D and Q. So we already have several semantics, several work about this semantics. And first of all, Badescu et al. Has observed that in their domain theoretical framework, they could not give a good semantics for this kind of program. But there are other work that's Ying et al., done by Ying et al. And Sabre et al., and both of them could define the semantics of this kind of program using infinite dimensional Hilbert spaces. And the difference is that with the semantics defined by Ying et al., we cannot know how to implement this program, but Sabre et al. Observed that they can know how to compile this program with using a list of qubits. So we want to focus on the work done by Sabre et al., which has implementation, but they had a limitation that in the program M, which updates inside the quantum while, has to be unitary. And the question we want to address is this. Can we remove this limitation of M to be unitary by applying our technique and move the measurement to the outside? Yes, why not? So what we're going to do now is to transform a program which has a quantum while with measurement into a language defined by Sabre et al. So Sabre et al. Use a language which has quantum control recursion and list of qubits. So the algorithms. So let me move on to the algorithm. The source program is quantum while, and in the first step we applied our technique to this M. So applying our technique, we get a program which consists of three parts. The definition of initial states, followed by unitary part, and followed by measurement. So what we can learn from this program transformation is that we get a program n bar, which we can consider it as a unitary part of this program. And so we want to translate this quantum while into a language defined by Sabre et al. And the key idea is to prepare the list of these Q's and A's and apply this n bar at the ith iteration, so n bar to Qi and Ai in the ith iteration. And so Yeah, so, and we also want to move this measurement to the outside of quantum while. So this is the translated program, which consists of two parts. And the first part is the definition of a recursive quantum while loop, recursive quantum program, which is a helper function. And the second part is how to run this program. So we prepare the list of Q's and list of A's. And in each iteration, we apply n bar in this recursive function. And to run this whole program, we first prepare the list of zeros for this LQ and LA. And then we execute this recursive function. And so we had to measure this AI. So we measure this LQ after running this recursive function. So what we can get is that we could translate the quantum while loop with measurement to the sovereign et al.'s language, which we can say that we can add the line which says, we can add this line. Right, let me summarize our proposal. So we propose a program transformation technique which moves the measurement inside a quantum to the outside. And what we get is that we get physical implementable semantics, and we could found a connection between Ying's work and Abbott's work, which is trivial, which is untrivial. And so we have also showed that our technique can also apply to quantum while. For the future work, we want to focus on the special cases in our technique and Abbott et al.'s one. So in our technique, there are some cases that we don't need to introduce dummy values, which is the case which looks like this, which means that we measure the same qubits in den calls and else calls. In that case, we just need to move this same measurement to the outside, which makes no type error. So it means that we don't need to introduce dummy value, which means that our semantics is unique. And there's also a special case in Abbott et al.'s work that in that work that they have observed that in a case the den calls and else calls consist of the same channels, which we can, but we can change the order. And in that case, the semantics is unique. And so we want to think about, we want to observe any relation between these special cases. Yes, so that's the end of my talk, and I appreciate any comments. Yeah, thank you.
All right, thank you very much. Questions?
I have a question because I read the work of that you mentioned about Sabri et al. Mm-hmm. I don't remember exactly this work, but what I remember is that in that work, basically they only consider finite recursion because they made recursion on list.
Right, that's right.
Yeah, so I was wondering, how do you want to manage the fact that a quantum while basically could be also unbounded, or you have to put some boundary to make this transformation?
So in that work, yeah, that's true, and they have another limitation that the quantum while loop has to known to be terminate, and it means that we have to prepare. We don't need to. We have to prepare infinite lengths of quantum cube if it's not known to be stopped. I mean, that's true. And yeah, so we can say the same thing for our work. It means that, I mean, so if we don't know if this quantum while terminates, then we have to prepare the infinite lengths of list, infinite lengths. Yeah, list of infinite lengths, but yeah, so we have the same constraints on our work.
All right, so it's like that you basically fix some bound, and the bound is the length of the list, of the initial ancillary list basically. You use the ancillary list to fix the bound, the additionally qubit to fix the bound of the loop.
Yes, that's right.
Right,
That's
thank
right. Exactly. Thank you.
Yeah, just to make sure I understood it, the technique of the dummy value, this is basically re-preparing the same state that would have been inside the quantum condition.
No, so we don't know what kind of state this P0 has, so we just need to choose an arbitral state, which makes our semantics arbitral. Does it make sense?
Your semantics are what?
So our semantics also have some kind of parameter, and yeah, as well as Yang's work. Well, but then the original parameter is different, but yeah, we also have a parameter, and we need to choose an arbitral quantum state here. Does it make sense?
Okay, but you're not necessarily having the same semantics as the untransformed program. Is that?
So, I mean, we don't know any semantics for the program transport the before one. So we need to choose to choose a quantum state to define the program, the original program.
Okay, yeah,
Thank you.
Yeah, I was also curious about the dots and the 0, 0, 0, because it did seem like it had an M in it. All right. Thank you very much.